Hi. In this lecture, we will show how the laws of electromagnetism predict electromagnetic waves. So this lecture will give us the mathematics of how that is a consequence from Maxwell's equations, which embody the laws of electromagnetism. Okay, so to get started, we will work in a vacuum, at least for this lecture. So that's basically in a region of space with no electric charges present. So the electric charge density rho is 0. And there are no electric currents. So the current density J is 0. So we'll work in that region, a vacuum, to simplify things. And okay, let's start first with Maxwell's law, also known as Maxwell's law of induction, where we have shown in another lecture that the curl of the magnetic field, curl of B, can be related to the time derivative of the electric field at that point in space, multiplied by these electromagnetic constants, mu naught and epsilon naught, the permeability and permittivity constants. So let's start there, as derived from vector calculus. And now let's take the curl of both sides of that equation. So we're going to do del cross to both sides of the equation. So that's the curl of B on the left side. And then we have mu naught epsilon naught times the time derivative of the curl of the electric field E, the curl of E. So we've just taken the curl of both sides. Now, it can be shown in vector calculus that the curl of a vector function can be related to the gradient del of the divergence of that function, or that field, B, minus del squared B. And what is del squared? That is the Laplacian operator. That's like the gradient dotted with itself. And so it's a scalar operator. It doesn't return a vector direction. And it's two derivatives. It's d squared dx squared plus d squared dy squared plus d squared dz squared. That's what the del squared or the Laplacian means. So this is stated without proof from vector calculus. However, I leave it to the reader. It's fairly straightforward to be able to prove this to yourself if you just write it out in detail what each of those terms are. And then basically simplifying the expression. So you can do that for both sides and show that that is a true statement. Okay, so how does that help us? Well, that tells us that this curl of B on the left side of the equation can be replaced by what's here on the right, and it has the gradient of del dot B in there, for example. But using another law of electromagnetism, Gauss's law for magnetic fields, even not in free space, even if there are electric charges present in currents, the divergence of B is always 0. So this term here is 0. So what I have on the left side is just going to be minus del squared B. Now Faraday's law for the right side, the curl of E, is equal to minus the time derivative d dt of the magnetic field B. And there's another time derivative already there, so it's going to give me two time derivatives. So I have, I'm putting into here that curl of E is going to be minus dB dt. The left side here is going to be reduced to, because one term was 0, just minus the Laplacian squared, or Laplacian of B. There, and that's the left side. So what am I left with? I'm left with that, if I cancel the two negatives on both sides, just turn them in, multiply by minus 1, for example, that the Laplacian of the magnetic field B equals mu naught epsilon naught, that's where they were there, d squared dt squared of B, so two time derivatives of t. So in other words, I have a second order differential equation on the left in space in terms of x, y, and z, and two derivatives of time on the right, again, two derivatives on t. So this is a second order differential equation solely for the magnetic field. The electric field has been eliminated now from Maxwell's equations, and this is only an equation for the magnetic field. And it's a vector equation, right? B, the magnetic field has x, y, and z components. At least that's one way to express it in 3 dimensions. And so this is a differential equation for each vector component of the magnetic field. It has to solve this equation. And we'll come back to that in a moment. So that was for the magnetic field B. What about the electric field? We eliminated it. Do we have no statement about it? Well, of course, that's not true. Let's work this around a different way, and we'll get a similar equation for the electric field. So that's the next slide. So this is one result to remember for the differential equation for B. Moving on to the electric field. Again, we'll solve this in a vacuum where there are no electric charges present or any electric currents. And this time we'll start with Faraday's law, which says that the curl of E, at least in differential form, is equal to the negative of the time derivative of B, the magnetic field. So we just work from similar laws before, but different swapping the order of the fields. Again, let's try this mathematical trick to take the curl of the electric field in this case. So it's del cross E on the left side, and then I have minus d dt of del cross B, or the curl of B on the right side. We're going to use the same vector calculus proof as on the previous derivation. The curl of E can be written as the gradient of the divergence of E minus the Laplacian of the electric field E. Again, this is the Laplacian operator, at least in xyz coordinates or rectangular coordinates. And again, since we're going to work where there's no electric charges present, just like for the magnetic field, when there are no electric charges present, then the divergence of E is also 0. So that term there goes to 0. Right? And so on the left side above, I just have minus the Laplacian of the electric field. And that has to equal the negative time derivative of del cross B. But from Maxwell's law, the curl of B is mu naught epsilon naught times the time derivative of the electric field. So this part up above can be just re-expressed as mu naught epsilon naught dE dt. So that's inside the parentheses what that equals. So putting that all together, we have, again, canceling the minus sign that's on both sides of the equation above. I have the Laplacian of the electric field equals mu naught epsilon naught times 2 time derivatives of the electric field. So again, it's a second order differential equation, completely analogous to what we had for the magnetic field, but also for the electric field, for each vector component. So every component of E must satisfy this equation. So we've again shown now that of the differential form of the laws of electromagnetism, that we get these second order partial differential equations separately for the electric field and for the magnetic field. They both have to satisfy this relation when we're in a vacuum where there are no electric charges present and no electric currents. Okay, this has some interesting implications, maybe profound implications, you might argue. What are those implications? Well, that form of the equation is known as a wave equation. And so that was basically telling us that there are electromagnetic waves coming out of Maxwell's equations. Both the electric and magnetic fields separately satisfy a wave equation of this form. So if I just generically denote E or B for the electric or magnetic field as F, the form of the equation was the Laplacian of that vector field is a constant times 2 time derivatives of that electric field. And I've written the constant in a way, very suggestive way, 1 over v squared. This relates to other wave phenomena. Just to remind you that the Laplacian on the left side are these sums of second order space derivatives, d squared dx squared, d squared dy squared, and d squared dz squared. And 1 over v squared, that will equal the equation I just showed you before from the last 2 slides if I write v as 1 over the square root of mu naught epsilon naught. Those are those electric permeability and permittivity constants that come out of electromagnetism in vacuum. So apparently we're getting a speed which is equal to 1 over that square root of the product of constants. And the solutions for this equation can be shown to be traveling waves moving in 3 dimensions with this speed v that's predicted here from the laws of electromagnetism. What is v? Well, if you plug in those permeability and permittivity constants, mu naught is 4 pi times 10 to the minus 7 in SI units. Epsilon naught is 8.85 times 10 to the minus 12 in SI units. We take 1 over the square root of that, and you get 2.998 times 10 to the 8th meters per second. So about 3 times 10 to the 8th to pretty good accuracy. And that's known as, or at least abbreviated by the letter c, and that's known as the speed of light. This is the speed of the electromagnetic waves, and light, just to jump ahead, is a form of electromagnetic waves. So Maxwell's equations are basically telling us let there be light. It's a traveling electromagnetic wave, and it has this speed, 3 times 10 to the 8th meters per second. It's a very large speed, of course. And what's kind of interesting is it only predicts the speed, right? There's not different speeds depending whether your source of waves is fixed at stationary on the surface of the Earth or on a rocket moving at a good fraction of the speed of light. It always predicts this speed, and that has an interesting consequence that we won't discuss here. It's maybe for a separate class or at least separate lectures, and that is Einstein's special theory of relativity. But as I said, that's another story. What we wanted to conclude here is the differential forms of the laws of electromagnetism, when combined, lead to these wave equations shown here. And the solution to the wave equations are traveling electromagnetic waves, or traveling waves, for the electric field and for the magnetic field. They each are traveling waves. Now they're not independent. Even though those equations were independent, separately for E and separately for B, recall that the original differential equations related like the curl of B to the time derivative of the electric field, and vice versa. The curl of E related to the time derivative of the magnetic field. So E and B are actually related. And that's a separate lecture, show the consequences of those relationships. But this was the point of this lecture, was to show you that Maxwell's equations in differential form predict traveling waves. Okay, we'll stop there.